All right, chapter 12. This is adaptations in aerobic and anaerobic training. Now, we're going to spend 3/4 of the time on aerobic. We've already kind of talked a little bit about anaerobic training already, like what your muscles do to adapt to that. And it's several of these things we've also already slightly touched on, but we're going to kind of put them all together into this is how we get into shape, is pretty much the point of this entire chapter here. So I'll say we're going to spend most of our time on the aerobic part here. We'll do a little bit of anaerobic, and then the last two things are about these two. I'm not sure where the cross-training one is there, but we'll talk about that one too, if we get that far. So this is the chart. This looks like Super Mario Brothers. This is all the reasons that your body goes through that improves your VO2 max. So, I mean, we're going all the way into some hormones here. We've got, hypertrophy, your blood volume. So we're going to talk about all these things, at least to some degree, and some of them we've already kind of gone over. So just a preview of coming attractions. We're going to come back to this just so you're like, hey, it looks like Super Mario Brothers, or how you skip all the things in a video game. You guys probably don't remember those days where you would get like a guide. You actually had a Super Mario Brothers guide that would tell you the best way to get through stuff, or the old Game Genies. That's another one you probably don't remember, but you would actually stick one thing in the cartridge thing of your Sega Genesis, and then you would stick the cartridge on top of that, and it basically would allow you to put cheat codes in. So I was like, this is kind of the cheat codes to why your body does what it does. So we start out with cardio adaptations to aerobic training, cardiorespiratory endurance. So what is cardiorespiratory endurance? The ability to run longer, basically, is what that is. The ability to sustain prolonged dynamic exercise. It's going to use all the major muscle groups, your cardiovascular, your respiratory, so heart, lungs, muscles, and the chemistry of your body, all doing that, are all going to go up in part of that. You need something? Okay. So your endurance training, I know this was a shocker here. Maximal endurance capacity goes up with your VO2 max. Shocker. Thank you. I was hoping for applause. I'm just kidding. So really, that's to say, the point of this is why. So you lower your heart rate to the same submaximal exercise intensity. So as you do like a 70% test, the higher your endurance gets, the lower your heart rate is going to be at that 70% mark. So that's something I'm going to do next quarter in my fitness class. I forget what they call it, or what we're calling it here. But basically, weight training, but upstairs, is they're going to do figure out your heart rate, figure out your 70%, and then you're going to try to run at 70% for 20 minutes, and they're going to have to keep their hands on the heart rate thing. What is your heart rate during this? So and then later on, they're going to try it again, and they're going to see if their heart rate goes down. So we're going to do some of these in my classes here. What happens when the exercise phys teacher teaches those classes? I have pre-made groups of people to study. By the way, the most studied population is college males. I don't know why it's males, but that's the most studied group. Again, so very simple. When pre-training, this is where they were. Post-training, their VO2 max went up. Very difficult, probably the simplest thing we're going to have in this entire class here. So this guy basically says the exact same thing. The video guy says your VO2 max is going to help your sport performance in pretty much every sport. So here are the big major adaptations here, and this is just an overview. Your heart size is going to get slightly bigger. Now, this is very minor. It's not like overgrown heart syndrome, but it's going to get, the muscles themselves are going to get thicker walls, so it's going to grow a little bit. The stroke volume, every pump of the heart is going to pump more out of it. Your heart rate is going to increase. The cardiac output, so how much blood is pushed out every single pump, is going to increase. The flow of volume is going to go faster. Here's the one that's a little different. Your actual amount of blood goes up. So the actual number of cells, the actual volume, the actual liters of blood in your body goes up, and that's some of the adaptations of your actual, like, red blood cells don't go up. They actually go down a little bit, technically by percentage. But your red blood cell volume actually goes down slightly, but that's because other things are increased in the fluids of your body that are getting pumped through. So there are some great numbers here. I actually gave somebody an extra point, if I remember right. They've had stroke volume times heart rate, and they put VO2 as the answer, and I think it was supposed to be like aerobic volume or something. And I'm like, yeah, that's what I would have put. So I gave somebody that on the test when I was grading here. So your O2 transport is your volume of oxygen, stroke volume, heart rate, and then the atrial and ventricular O2 difference, so how much that is in there. Your VO2 max goes up, your max stroke volume goes up, the max heart rate goes up, and then the difference here is probably the most convincing one that's going to be there. And that's what they were testing in this equations here. So as we're saying, the heart size actually increases, not much. So your heart mass goes up partially because there's going to be more blood in the heart every single pump. So the target pulse rates, cardiac hypertrophy, as in the muscle gets slightly thicker, and that increases your stroke volume. The big thing that adds to your volume of blood, as I said, you have more blood, is you're actually going to gain plasma in your bloodstreams. So that's why I say your blood actually increases the amount when you're exercising. So it's not a ton, but it is more, and that's part of the reason that your blood pumps faster. And part of the reason you get worried when somebody already has high blood pressure and then they start exercising is now they have more pressure added because there's more stroke or more pressures in there, and you just don't want them to blow something that they shouldn't. So this is the difference in percentages for 3 different groups. Here, the strength athletes are in yellow, cyclists are blue, runners are in red. And this would be the left ventricular internal diameter. So this is the difference amount of controls. The left ventricular one here, this is the wall thickness, median wall thickness, so how thick it is there. Cyclists are a little bigger than runners, kind of surprising. But more surprising to me, the strength athlete and runners are fairly close. I would have thought that the thickness of the heart wall would have been, the cyclists and the runners would have been similar. Is that because when you're running, your heart's bouncing around? I don't know. But it's just kind of like, I would have expected that to be different. And then left ventricular mass, now it's a little closer to what I would have expected, where strength athletes compared to runners. So some interesting things there about the size of the heart, or thicknesses of the heart walls. I say there's different walls that they were testing there. So as I was saying, your stroke volume goes up after training. Part of that's because stroke volume increases when you train. Your end diastolic volume goes up, so at the end of the pump there, and then the preload actually increases. Your resting and maximum heart rate go down. Let's say we kind of tested that by people's heart rates being lower, and that's also because their end diastolic volume goes up as they press more out. Left ventricular mass increases with training, and that's what they were testing right here. Left ventricular diameter, or left ventricular mass. Here we go, sorry, that's this one. So that's what they were testing there. So the stroke volume adaptations tend to decrease with age, as in the older you get, the less it actually, the stroke volume doesn't happen as much the older you get. So the younger you are, the better that's going to be. Same basic concept here. This one they were testing how much stroke volume they had pre-training compared to post-training. And let's see how far was this one here? This was just a walking, jogging, running on a treadmill at different velocities. So how they tested that is, I would really want to know. How do you test how much stroke volume the heartbeat has while you're running? Seems a little weird, but it's possible, apparently. So here's how much the blood is in your body here. So the untrained person is going to be 50 to 70, and their max heart rate is going to be 80 to 110. A highly trained person, their stroke volume, so this is milliliters per beat, is 90 to 100 milliliters, and they could have up to 220 milliliters. And I'll talk about that in a minute. Other things that your heart does, your resting heart rate goes down, your submaximal heart rate will go down, and your max heart rate doesn't change, or max heart rate doesn't change a ton with training. It actually has more to do with age. So that's why when they say, what's your maximum heart rate? 220 minus your age is your max heart rate. So most of you are going to have a max heart rate of about 200-ish because you're all around 20-ish. I'm pushing closer to 40 now. So my max heart rate is about 185-ish. So, and I have definitely noticed that the more I've gotten into running with like smartwatches, I'll be like, why am I so tired? Or even just like hiking yesterday. I had my son on my back and I was hiking back in the back 40 to try to put him to sleep. It did not work. I'm hiking around the back 40 and I'm looking at my watch. I'm like, why am I so tired? And I look at my watch, 160. I'm like, okay, I'm 20-ish beats from my max. No wonder I'm so tired carrying a 25, 30-pound child on my back going up a hill. I'm like, that doesn't feel like it should be that difficult, but it was. So same kind of things here is your amount of volume there. Oops, is that over here? Never mind. Same basic concept. Heart rates in beats per minute to treadmill speed. Your heart rate was lower the higher or after post training. So some other things here. The heart rate and stroke volumes kind of interact. So how fast your heart's going by how much it's pumping. So the heart rate's going to be lower and the stroke rate goes up. Yes, it does. Spoiler alert. So you also will recover quicker. When we do our VO2 max test, when you say, I'm done, somebody has to hit the stop button or slow the treadmill down, and another one has to hit the end test, and then it's going to say recovery. And then it'll keep measuring how fast you recover for 3 minutes as you walk. And it's going to see how fast your exchange is back and forth and your heart rate. How long does it take for your heart rate to get back? So it's actually going to give you, as a part of your VO2 max test, it's going to say, here's how fast you recover. So that's another useful information. Heartbeat times time. So as they were training, it goes up. And then the recovery. Notice the post-training, their heart rate decreased a lot quicker in comparison to before they started training for, I forgot how many weeks was on this. 8 weeks? Nope. It does not say. Gotta love it when it does that to us. Same concept here. So this would be cardiac output, which is heart rate times stroke volume. Again, it goes higher liters per minute after training, and most of these I think were an 8-week program that they did. So it didn't take super long. So in a 1/4 class, you could increase quite a bit if you go from not exercising to exercising consistently. And I noticed that in myself in college when I took the weight training class, the adaptations my body did. I gained 15 pounds of muscle by being forced to be in the gym for a semester 3 times a week. I was like, yikes. I'm like, I wish I could have stuck with that a little better. So there's little or no change at rest in your cardiac output or during submax training. So like at a 50% or 70%. Now it's going to go up a lot when you get to your maximum trainings. A little more on the cardiovascular. Your blood flow is going to increase when it gets to the exact muscles. The capillaries and the capillary recruitment, they're going to be increasing there. The cross section for that exchange, so the ability to get oxygen to the muscles, that exchange goes up the more you work out. The blood flow will actually decrease to the areas that don't need it. So if you're running, your heart, your legs are going to be getting most of the oxygen. Your arms, not as much. So your body actually, have you ever seen some of these new cars that have electric systems in it? And they'll be like, it takes the power from these to these. My car is all-wheel drive, and when you start going up a hill, you'll see it change from the front wheels only to all four wheels as it goes up. And then when you start going down the hill, now it's only putting power to the front. Your body actually does that to whatever muscles are being used, which is a really cool thing. I'm saying the total blood volume goes up, which is going to prevent decrease in the return to the body as you are running and such. Again, total volume goes up, so you're going to add plasma proteins into the blood. Water is going to go up, as well as, I believe that's sodium retention. And this will all happen in the first couple of weeks. This is when this is going to keep increasing there. So red blood cell volume is actually going to go up a little bit, but the hematocrit actually goes down, and that's just because of the percentages. I'll show that in a graph in a minute. And the viscosity is going to go down, so it's going to get loose. Things are going to slide faster through your veins rather than being bogged down. So here's your stroke volumes compared to their VO2 max. And then here's the red blood cell volume compared to their VO2 max. So a lot more differentiating here between the individuals in comparison to their stroke volume. So how much red blood cells. So here's the graph I was saying about why what happens to your body when you start exercising. So when they were training, they had a total of 5 liters of blood in their body. Post-training, they had 5.7 liters. So it went up by 0.7 liters. That's 600 milliliters. So that would be like almost a 1 liter water bottle. That's quite a bit of difference inside of your body. So the red blood cells go up a little bit, so 2.2 to 2.4, but the actual hematocrit compared to the amount of body fluids actually goes down a little bit. So it's like more red blood cells, but less in proportion to the whole body there. Standing break. Moving on to the lungs. Where was my story here? Nope, can't find it. All right, so there was one thing I was going to mention. I just can't find the notes that I put on it. There is one problem that you would want to brag about. So a highly trained, and we're talking marathon runner level, elite marathon runner. That guy who did under 2 minutes or under 2 hours here recently at the Boston Marathon. That kind of level. They do get to the point where the blood is moving so fast because the stroke volume of the heart is pushing so quickly and so efficiently that the capillaries in the lungs cannot keep up the exchange of oxygen and carbon dioxide. I forgot what the actual term is, but there is an actual term and a possible problem of your heart is so efficient that your lungs and capillaries cannot keep up with the amount of blood that is going past them. And so that's kind of like the absolute limit of what your body can do, is when your heart is pumping so quick that it can't keep up the oxygen and you have to slow down. So it's possible, it's really difficult. It's one of those kind of weird exercise physiology things that we talk about because it doesn't happen often, but it is possible that your heart is too strong. All right, so we're moving on to the lungs now. So there it was. It was, of course, on the next slide. Exercise-induced hypoxia, as in there's less oxygen in the blood. That's the term. So your pulmonary ventilation is going to be lower at its given submaximal intensities. Yep. It's going to increase at maximum intensity due to the total tidal volume of the respiratory frequency, as in the tidal, how much air is coming in and out each breath. The diffusion at the end where the capillaries are remains unchanged at rest and at submaximum, but it's going to increase with the closer you get to max intensity and maximum lung perfusion. So the arterial venous O2 difference, so as the oxygen goes in, how much is getting diffused and coming back in through the body there and through all the blood. Active blood flow, there we go. Here's an interesting question. Elite swimmers, your Michael Phelps, Katie Ledecky, forgot who else is the big swimmers right now. They have tested that their lung capacity is bigger than the normal person. Is that because they train and that makes them bigger? Or are they born with bigger lungs? They don't actually know. That's an interesting kind of question mark there. Because if you look at Michael Phelps, that dude is a freak of nature. If you look at all the measurements he has, his wingspan is like 6 inches longer than his height. His feet are like 5 or 6 sizes too big. So he's got like a size 18 shoe or size 20 shoe, and he's 6'5". It's something crazy like that. His hands are bigger than they should be. His lungs are bigger than they should be. There's a question, so it's like, is that genes? Or is it because he's been training since he was, in diapers almost, it seems like. They don't actually know the correlation between lung size, hereditary, and training. So we're talking about how much air they can blow in and out. So those tests that we were talking about where you put your mouth on a thing and blow it into it, when they test elite swimmers, they just don't know. But all they know is the more you train, the more air that you're able to get in and out. So there is some that can be done with training, obviously. But when you get those elite swimmers, do they get there because they train that well or because their lungs are already big enough to do so? Just an interesting kind of question mark there. So this is one that I'm not as familiar with. I tried to look it up a little more here right before class. Is they have this, I don't even know what they called it here, hormone that they found. And it came from a Parkinson's research, as they were trying to figure out, is there a way to delay Parkinson's? And they almost, as the guy put it, stumbled on this PGC1 alpha, and you could try to pronounce all that. And they called it the master switch for energy production. So they found this hormone was higher during some exercises. And so when they tested everything out, they called it the master switch for getting things to work. So this was integral in mitochondrial biogenesis, is what they called it. And so it's going to activate these 3 pathways. We haven't quite talked about all of these. I think I looked up this kinase one here last year, and it just didn't come. I didn't get far enough into it. And there was an entire several papers published about this. So what they were saying is when you start doing endurance training, you're going to increase calcium. That's where this calcination here. These 3, which came from over here, all tell this hormone to run, and that's going to tell this hormone here tells your body to switch from fast to slow twitch fibers. It's going to tell the body to increase the health of the mitochondria, which is where your ATP production happens. And it also is going to tell the oxidative system to keep creating more ATP. And that's what's going to improve the muscular endurance of your body. So it's a really interesting one that I have not had enough time to really look at. But this is one of the more recent things in exercise physiology. So as we were saying, so this is why your body is going to start using different muscle types. So you increase the size and number of muscle type 1 fibers for your endurance type exercise. Capillary supply goes up, the myoglobin's going to go up in the blood, and the O2 delivery to those mitochondria to get more ATP, to get more energy. So increasing that mitochondrial function is going to give you more mitochondria and more energy that's going to come out. So magnitude of change is depending on the amount of training that you do. This is also part of the reason that the muscles, it's really hard to be an endurance athlete and a strength athlete at the same time. Because your body goes, oh, we need to change the muscle type from type 2 to type 1 so that we can do the endurance things. And they may actually be type 2X, type 2A rather than type 2 to 1, but that's another one there. That's a fairly recent thing as well in the last 10 years. I was talking to one of my old students from Lodi. He was at their alumni game that I went over and refed. And oh man, the alumni that I used to coach killed the current team. It was like a 40-point blowout. I was so happy. Well, because like the guys I coached are better than the ones that, anyways. But this dude, he's at Point Loma University in like SoCal, and he's like, yeah, I'm taking exercise science, and he's like, yeah, I have this teacher that's like a fitness buff, and his goal is to be able to run a like sub 4:30 mile and be able to squat. I forgot what the number was. Some powerlifting. So basically, he's trying to power lift and be able to distance run to the same goal in the same day. I'm like, that's some and this guy's, I've emailed back and forth with him a couple times. Like, the guy's got a doctorate in exercise science, basically. So he's trying to like experiment on himself. And I kind of want to go back for that alumni game again, just so I can ask, how's that guy's training going? Or maybe I'll just email him. But it's just kind of wow, that's really, really hard to confuse your body that much. All right, and here's a little bit more of that PGC1A that they were talking about here. So as you exercise, that PG1A is going to do all this stuff, telling about the good mitochondria, and it's going to work those things to give you more ATP production and more energy. And so the changes in your VO2 max, depending on how many months you train, notice that it goes up really heavily in the first 2 months. But then it kind of plateaus off, but you can still continue to increase it. So you're going to have a change in your, this is succate dehydrogenase. Total distance per day that they are able to do. And that has to do with these as well. These could all three probably be in the same chart. And here's that same succate dehydrogenase on the untrained, the joggers, and then the highly trained marathon runners. So this is another one of those things they've tested in their blood to see where it level is. Same thing, citric synthase. And those are all kind of here's the next kind of major part. Your lactate threshold is what goes up right before you can't go anymore. So kind of your VO2 max and lactate are kind of related together. The higher your VO2 max, the higher your lactate threshold is generally going to be. And that's also related to your respiratory exchange ratio, which we could also too. And this is dependent on how much fat compared to glucose that your body has in there too. So here's what that would look like in a chart. Here's the blood lactate concentration where it spikes. That's the lactate threshold. So an untrained person is here at about 60% of their VO2 max, if we're being nice. A trained individual, they can make that lactate threshold at 80%. So the more trained you are, the longer you can go in that basketball game, that volleyball game, football games, probably mostly for your track and field and cross country. The higher your lactate threshold, the longer you're going to be able to run, which is why you won your race. Same concept here, blood lactate concentration, and this is a treadmill speed compared to your VO2 max. Same concept. Untrained, trained person ended at about 9. This person made it to about 12. So your resting and submaximal VO2, the resting VO2 is going to be unchanged, oddly enough. So when you're not moving around, VO2 max, or your VO2 doesn't actually change no matter how trained you are. Your submaximum also, so if you're running at 70% or 50% or whatever, it's not going to change that much. And in fact, it actually might go down with your VO2 max, and that's because you're getting more volume in there. Max, on the other hand, can go up quite a bit, 15 to 20% with training. So that's going to be due to your cardiac muscles being able to add more and the capillary densities in your lungs and in your to be able to get those things out there. So back to the Super Mario Brothers. So we're going to start over here. So we said just on the last slide there, your capillary numbers go up. How much recruitment they have. Your mitochondria are going to go up from that fun hormone that we talked about earlier. And you're going to increase the myoglobin in the blood. Your metabolic things are going to increase. And so that's going to give you more blood flow. The atrioles are going to be inactive to the areas that don't need it. And they're going to be redistributed to the muscles that are moving. And that's going to make all these things go up here. Your lung volume, or left ventricle, is going to go up. Your plasma volume goes up. So that's going to make you have all those things combined together are going to give you more stroke volume, which is going to give you a higher blood movement through the body, which is going to give you a bigger VO2 max. Complicated, but it's as uncomplicated as you can make it in a graph. So you just kind of have to keep read things. Or what terms do I remember from this? And this is also in your book, and it'd probably be a bigger and easier to read because this is not the clearest picture. So you will have some long-term, how am I doing on time here? So long-term improvements is always at best. Your highest possible VO2 max is going to be achieved between a year and a year and a half. Performance can continue to go up, but eventually it will kind of plateau because you can only go so far in your training there. And then you have to start coming up with other things to increase it, which is part of the reason why people turn to alternative methods like steroids or whatever was going on in cycling here a few years ago, where they were doing kind of a blood thing, where they were blood doping, because that would give them more hematocrit to move more oxygen, which would make them increase their lactate threshold, which would give them a higher amount of energy to be able to keep going. So that's why blood doping is illegal. So factors dictating the individual responses. By the way, if you want to know more about that, there's a really cool documentary on Netflix. It's like a one-word thing, it's like Brodus or something like that. And it's the guy who figured it out at one of the Olympics, how they were cheating the system. Like it had to do with how they were putting on these things, and they would pour them out and then put different ones in so that they could keep blood doping. And that's why the Russians are still not allowed to compete in a lot of the Olympics. It's all due to that guy finding it. So it's a really fascinating thing to look at. I watched it on a plane flight once. So here's your oxygen uptake compared to how fast they can go. So at 88% of their VO2 max compared to how fast they were going. Changes in race pace continued after training, after maximal there. And we can do your VO2 max test on a bike if you want. Most people do it running. I like doing it on the bike, but that's because I've got ankle and knee issues that make it. So if I want to get a better version of it for myself, biking is the best way to do it for me. So training status versus and pre-training VO2 max. A more sedentary individual is going to have a greater increase. A more fit individual is going to have less. Heredity also, we kind of mentioned that earlier, and we got a really interesting one here coming up about twins. Like if you have twins both exercising, will they have the exact same response? What do you think? Similar, but still different. That's the interesting part, is everybody is different. So VO2 max is similar for identical twins, is more similar with identical twins than fraternal twins. 20 to 50% of your VO2 max variance would be due to heredity. So it's really, if you want to be the best distance runner, choose your parents wisely. That is going to have the biggest difference on your max VO2 max. Is going to be heredity is the biggest part. And that's why I asked earlier about, are your lungs bigger because of heredity? Maybe. So here is the twins here. So non-twin brothers are the triangles. And you can see those are pretty far apart. The yellow, or the red ones, are identical twins. And are twins but not identical would be red. And the blue kind of ones are identical twins. So there's less variance from the line with the identical twins than the non-identical twins. The one with the high metabolism is got the gene luck. As I say, heredity has a lot to do with it. And that's why studying twins in this area is really interesting. Are you identical or not? Okay. So it's just genetic luck. And you can't do anything about that part. You can train it out to a point. Like if your sibling, let's say if they're totally sedentary and you're super active and you're trying to train to run 5Ks and half marathons and marathons, you might surpass them in your VO2 max. But like my wife, she can train for 3 weeks and lose 15 pounds, and she only weighs like 150 pounds at most. Or right after pregnancy, a little bit of exercise, and she dropped all the pregnancy weight in like a month. It's like, that's not fair. She can have a six-pack by starting it at like spring break and be like, all right, before summer, I want to make sure I'm in shape again. I'm going to work out for the next 2 months, and she'll have a six-pack. I'm like, that's just not cool. I will never. But it's her genes. Once her body reacts to exercise, and it just, like, that's not cool. I cannot do that. No matter how hard I try, I cannot get a six-pack. It will always stay there. It's just not cool. I can train for 1.5 years straight. I cannot get rid of it. It's, ugh. So I'm sorry you lost the genetic lottery versus your twin. So there is a little bit of sex difference. So untrained females are going to have less VO2 max compared to an untrained male. And part of that is just by how your body is built. Men generally have a wider shoulder, which makes for a larger rib cage, so their lungs can expand more. That's very generalized, but like untrained versus trained. But you can make up for that. The trained female VO2 max is going to be closer to a trained male. So it's like your body can change that. So there's a bigger change in older men versus women. Older men have a lower VO2 max than women do. So it's like, it starts out bad for the females, but it ends up being bad news for the guys. The older we get, sorry guys. And this is what I was saying, the high responders versus low responders. I was a little bit ahead of myself. My wife is the high responder. I'm the low responder. So genetically determines variation in VO2 max for similar training. Physiological mechanisms and the reason for the tremendous variation in training outcomes depends on what you're going for. So here's that same thing in a sedentary person compared to a trained one. So this would be older men, older women, older women's here. That's not working right here. Older women taking estrogen. There we go. So basically after menopause is where it changes for ladies. Estrogen is required to elicit exercise training-induced improvements in vascular epithelial function in older postmenopausal women. That's what my note says here. In older men, moderate intensity exercise training significantly improves vascular function, and yeah, all those things there. Anything else in here? Wow, that is a very long note on that one. So training across sports. So we're still in the aerobic training here, and I'm running out of time. Basically, training for one sport can affect another. One of the guys I was researching this on, he was telling stories about he was a catcher on a baseball team, and most of the cross-country team was also on the baseball team. But they like for some reason, those teams seem to be not related at all. But for some reason, they would increase with each. Like your baseball players were good cross-country runners, so your training can cross between the two. Bed rest is very bad. I definitely noticed that when I had the health problems, I could barely run beginning of last year. When I started doing intramural basketball, oh man, I was walking up and down the court. It stunk, but by the end of the season, it increased a little bit more and a little bit more. And I really can't wait for this year because I want to see if I can beat my 38 points in a game. Because like I say, I scored more points than my age in a college intramural game. So yeah, all those things are going to go down when you are, what's really fascinating on this one, and we're going to have to keep going here, is when people are astronauts and they're weightless, now they don't have gravity pushing on their bones and their muscles. And when they got out of being at like the International Space Station for several months, they can't even walk. They have to be carried because their body's not used to gravity again. So their muscles degenerate when you don't use them because you're weightless and you're pulling yourself through. And there's been studies done on astronauts, like they purposely put them on like bungee cords, bungeeing them down to a treadmill and making them walk or jog in space to try to keep their leg mass up so that when they get back, they can still walk out of the space shuttle or whatever they land in. We're going to skip that one. So anaerobic, we've kind of gone over most of this already. So that test that we talked about there, yeah, we've pretty much gone over this. Your PCR systems and your glycolic systems can all go up and get more efficient with training. And there's those two different systems. So creatine here is the first one in the first 6 seconds compared to the 30 seconds as it can be. These were 30-second bouts of exercise here. Your amount of power goes down depending on how much time you're going there. And they were measuring knee extension time, how fast you could use that there. One of the big things recently has been high-intensity interval training. Really good way to, time-efficient way to induce many adaptations that are similar to endurance training. So you can get a lot of the same adaptations doing high 100% sprints. And what I'd use I had the basketball team doing this earlier, is doing 20 push-ups, sprint down and back, and you try to do that in under a minute. And I always tell them, like, the faster you do it, the longer your break is. So they try to really do their push-ups really fast, and then on the minute, I do another one on the squats, down and back, sprint, down and back. And in 10 minutes, I can hopefully get as much of the endurance adaptations as if I have them go outside and run 2 miles. That's my goal. And that's kind of where this is all going. But here's the biogenics about it. So these high-intensity things stimulate mitochondrial biogenesis and changes in the capacity for carbs, fat transport, and oxidation. So those are the things that you're training when you're doing this high-intensity interval stuff. Don't do it only that, but as you're trying to get those adaptations in your body in a shorter amount of time. The more specific you are in your training, your body's going to adapt to that. Cross-training, that's what we were talking about a little bit earlier. Training different fitness components once or training more than one sport at one time. High schoolers playing multiple sports is a good thing generally. I love it when I have a player come in from playing like soccer and then they come to basketball season. because they're already in shape. Not sure if it's going to work as much for football compared to soccer, because football is a different training compared to basketball, and vice versa. So endurance benefits are not blunted by strength training, totally. There are some muscle adaptations and everything, but you're not going to like stunt your growth if you're doing strength training while doing running. And we'll go into that more in TNT of weight training. And I tried to show all the different numbers here as they get better with their anaerobics and aerobically trained. And that's all I got. Have a wonderful day. We get to chat more tomorrow. Is it Thursday?
No, today's Wednesday.
Today's Wednesday. We have class tomorrow. We have another lecture tomorrow.
We don't have questions, right?
No, because I got an observation to go to.